Matthew Russell. Matthew is the international sales manager for the Tintometer company based out of the United Kingdom. Matt is a color control expert with over 22 years experience in solving customers' problems globally. In recent years, Matt has focused on the edible oil industry and their practices and technologies concerning precise color quality measurement. Today, Matt is going to talk to us about what can go wrong when you measure color. So welcome, Matt, and I look forward to your talk.
Thank you very much, Larry. Good morning, good afternoon, good evening, everybody. It's a pleasure to be here, talking to you from Manchester here in the UK on a sunny day. Yes, I'm the International Sales Manager for Colour for the Tintometer Limited. I'm going to be talking to you about colour. Now, the first question I often face with people is, well, why do I need to measure colour? I've got eyes. I don't need colour measurement equipment. Why do I need to spend money with you? I found a recent quote which I think summarised very nicely the fundamental problem with that statement. One says red, and there are 50 people listening, it can be expected there will be 50 reds in their minds, and one can be sure that all these reds will be very different. This is from a gentleman called Joseph Albers, who was a big deal in the world of graphic design and globally. And I think he summarises the issue very nicely. We can picture a colour, we can look at a colour, whether it's a red or a yellow, whatever, but it's very difficult to communicate that and to control that. And what we want is data and numbers. You know, we've been talking about processes previously. They all require numbers, data. So we're all about data. So, colour of oils. We have a wide variety of oils in use all around the globe, different crops for different purposes, the more common such as soya, palm oil, but then the more exotic oils, and increasingly new oils are coming onto the market, but they all have something in common in that they're often refined and processed, and that process needs to be tracked. You have the deodorization, you have the bleaching of that process, where colour is a useful quality control parameter. Reason being, the appearance, obviously, of the oil itself, but more recently I've had conversations talking about how the darker an oil can affect its flavour and other important, you know, consumer parameters. So colour is a long adopted and well-used parameter and recognised for colour, for quality. The main focus in the oil industry is on redness and yellowness of the oil, and I'll go into that why in a little bit more detail later on, but I just sort of refer to you a couple of common standards that are used by the AOCS and the industry worldwide. The AOCS Tintometer colour parameter, according to well-established AOCS methods, looking at the redness and yellowness, and then the Lovibond red, yellow, blue neutral colour, again, well recognised and detailed in AOCS and other standards, which looks at the redness, yellowness, blueness, and neutral value of colour. As I said, we've been in the world of colour for a long time. Without going into too much detail about the history of our company, back in the 1890s, the founder of our company, Joseph Lovibond, built the first tintometer, looking at tint or colour. He took red and yellow pieces of glass of a variety of shades and realised that he could put a sample, originally developed for beer, put a sample in there, put the different red, yellow and red glass slides in of different, different lightness and darkness, and match his colour and get a number. And over the years, this visual method where a human operator would visually adjust redness and yellowness to match a colour. It's been through various different reiterations in the 30s, in the sort of 50s and 60s in the Model D, the Model E. There's still a few of these out there in the market. I believe people are still using them. The AF710, which is used in the United States, specifically for the AOCS tintometer scale. And then the Lovibond Model F, which is still commonly used in the edible oil industry all over the world. Basic operation of the unit, is you open that grey lid at the back, you pop the cell in with your oil in it, and you have a series of racks which you can bring into position by adjusting dials, and then you can look down the viewing tube and match the colour. These are the actual racks. If I can bring up a pointer here, I could just indicate to you, for example, what these racks are showing. So on the yellow racks here, we have steps of 0.1 of colour. So from 0.1 to 0.9, and then steps of 10, 20, 30, 40, 50, 60, steps of 1, 2, 3, 4, 5, 6, 7, 8, 9, and then steps of 10, 20, 30, 40, 50, 60, 70. So you can see that by positioning those racks in different combinations, we can go from 0 to 79.9. Same cases with the red, same as with the blue. So this, once you combine the red and the yellow and the blue together, you're getting a very wide gamut or range of possible colours that this visual instrument can factor in. The neutral there is to compensate for brightness of some oils. That's a different topic on another day. So basic principle, you have a human being, a light source, and a glass cell. The cell has your oil in it. You're looking through the cell, through to the lamp, and then you're introducing a series of different glass filters between the sample and you, matching the colour. And the operator, once they're happy that there's a visual match, will come up with a red and yellow value, and possibly a blue if you're using the Lovibond scale, and possibly a neutral, defining the oil. So you've gone from it's a yellowy browny oil to I have a precise, or have a number I can associate with my sample. And exactly, this is what you see through the Model F sample viewer. So this is important for our company, so much so that our logo actually represents the Lovibond red, yellow, blue colour scale there, with the yellow, red and the blue. So I talked about why this redness and yellowness, why is that being used, combination of that. What I have here is a CIE 1931 chromaticity diagram, which in simple terms is a map of human colour vision, what we can perceive in terms of the visible spectrum. The black triangle is effectively what you're all looking at, which is your monitors. Your monitors have red, green, blue guns or LEDs in them that combine together to give you all the colours you see on your screen. That's the map. It's a colour gamut. It's the possible max green, red, blue of your monitor. Now below that, in the slightly fainter line is the Lovibond scale. If I can, let me just get rid of my pointer. Yeah, it's gone. Oh, sorry, one moment. What I've got there mapped is the red shade from the red of the Lovibond scale, the yellow from the yellow of the Lovibond scale, and the blue. And within that circle is pretty much where most people are worried about in the edible oil world. The combinations of reds and yellows, the browns and oranges and yellows of edible oils. You know, a little bit of the green sometimes, but you know, broadly that's where everybody tends to live. So you can see from this scale, it's very useful because we can gather a lot of information, precise information about colour in that part of the spectrum we're interested in. Now, those of you more familiar with the Lovibond scale may have come across this common misunderstanding. We're used to linear scales. I've got a centimetre ruler here, 0 to 30 centimetres. That's a linear scale. The difference between 0 and 1 centimetre is the same as the difference between 29 and 30 centimetres. Because of the visual nature and the nature of the glass used in the original scale, the Lovibond scale is not a linear scale, it's a logarithmic scale, which means you have more precision in the lower values of the scale. And this has practical applications when you're measuring colour with regards to path length. If you're taking an edible oil, you put it into a cell, depending on the path length of the cell, it will affect the appearance of the color. Remember, we're talking about the visual appearance of the oil. If I take a range of glass cells, I put the same liquid reference in them, and then I look at them lengthways, you can see straight away, it's very obvious that a 6-inch cell appears a lot darker than a 1 millimeter cell. And this has a practical application. And this is why we recommend that when you combine the red, yellow, blue, or neutral values, you always try to have a number below 20, because you can reduce the path length. So for example, if I have a 5 1/4 inch cell with an edible oil in it, I'm measuring it in a color measurement device. I'm getting a value around 50 Lovibond yellow. That's actually, you're getting into the realm where you know, as a human observer, you would struggle to spot the difference between 45 and 55. So a way to improve your resolution on the reading is to drop the sample into a shorter path length cell where you will get a lower Lovibond value, but a more precise Lovibond value because of the nature of the logarithmic scale. And this is, again, often spoken about in the standards, but poorly understood. So I always, whenever I have opportunities like this, I like to raise this and sort of to my audience, just to say, you don't have to be locked into a particular path length. You can vary the path length, particularly with the Lovibond scale and the AOCS Tintometer scale, to improve the precision of your reading. And if you do have a Model E or a Model F and you're using it, always read the manual, because it stipulates this and makes this point I've just made to you about this 20 Lovibond units. Sometimes it's not practical. 20 is, difficult to achieve, but it should always be your goal. Now, we're talking about color measurement. If we're measuring the oil needs to be transparent. We want to get our light through the sample to the eye, in the case of a visual Model F. We don't want light scattering, because we're looking at turbidity then as another factor. So it's very important when measuring oils to get the samples transparent, either by filtering or heat. Now, with some oils like soya, oilseed rape, sunflower oil, they're nice, clear, bright oils, often at room temperature, 20, 25 degrees. But when you get into palm oils and some other oils, that can be a real issue. And that needs to be factored into any color measurement to stop variations in readings, not because of an actual color difference in the sample, but because of turbidity. Now, we talked about visual equipment, which is still commonly used in the market. But the key thing is that you have variation between observers. So two people in a laboratory may view an oil using a Model F, a visual equipment, or an AF710, and disagree with each other. And the standards, the AOCS standards, wisely refer to use of a third arbiter to check and concur which of the readings is correct, whether it's a pass or a fail. So it's a consensus. Unfortunately, many people are using visual instruments with perhaps one operator who has never been color vision checked, is perhaps unaware of the possible variation between them and another person. So the standards, the AOCS standards, recommend the use of at least 2 operators and a third operator when visually checking a system, an oil. In the AOCS standard 13E92, there's actually a table within that standard that stipulates the values that you can be measuring and the expected tolerance of those values. So if you're measuring an oil that's giving you a red value of 5, you can expect on the same equipment in the same lab between different operators to have a repeatability of plus or minus 0.7. In a different lab with the same oil, with another Model F, different operators, because of various factors, there might even be wider variation. And this is because you have a human being making a visual color decision. So the fundamental issue is the human being making a visual colour assessment. As I said, the methods have taken steps to reduce that, but you need to be careful. So let's summarise. Time and compliance. Compliance with a standard and time are the two key parameters in a lab or in a production monitoring process. In the past, to a certain degree, I would argue people had more time, therefore they could achieve high compliance, particularly with a manual instrument where they're having to take care in making adjustments, fine adjustments to get a colour value. However, in the real world today, we have low compliance and quick measurement. So people need to make fast colour measurements, but you know, because they're making sometimes having to make visual assessments and rush it, they have low compliance. This can be an issue. So this is why we've adopted automatic colour measurement, automatic spectrophotometry, where if you have an automatic system that doesn't rely on an operator making a visual assessment, you can have a fast measurement and a high reading, giving you high speed measurement and high compliance. So this is why, particularly in North America and South America, people have adopted automatic spectrophotometers like the PFXi. And increasingly, a new product, the Model FX. These operate as follows. You have a lamp, some optics, a glass cell, a detector. You shine your light through the liquid, your oil, onto the detector, and we convert that into spectral data, which we then can convert into a Lovibond value. If you take the Model FX, it's a benchtop unit, robust, tough for the environments that it's in. It's slightly more compact than a Model F, AF710 or a PFXi. But the key thing here is its accuracy and repeatability. And this can be any spectrophotometer, where if here in this, I have a spectral graph here showing transmission versus wavelength, visible spectrum, give or take about 380 up to about 780, where I've taken amber glass, which is a very stable medium. I've measured it in a PFXi, and for 30 readings, they're identical. If you were to take human beings with their variation and visual assessment, you would not achieve that. We can take a real world sample at a liquid reference in a glass cell and get the similar results. So it's not just a perfect sample. Now, in terms of temperature, as I've spoke about, the transparency of a sample can impact colour readings. Palm oils are particularly problematic, where we know, depending on the temperature, because of the multi-fractional nature of the material, depending on the different fractions, different melting points, it'll have different characteristics. That's why it's so useful. But we know with a palm oil, if you heat it, free samples there, room temperature, slightly heated, nice and warm, nice and clear and transparent. But the temperature of the oil directly affects potentially the readings you're getting. And this is why, particularly with our Model FXs, you have a thermometer in the device as well as a heater. And I'll show you some data proving why that is so critical. A series of palm oils here measured in a Model FX. What I'm tracking there is a Lovibond blue value versus temperature. Blue is often an indicator of turbidity. If a sample is showing a lot of blue and it's not green, it's appearing dark to the instrument because the light is getting scattered. Therefore, if we take a series of palm oil samples at 50 degrees, you can see that blues drop right down, which to all appearances, the sample is transparent. However, further analysis, by that, I mean, as you say, I want that. I want the green tick. If I put a piece of paper with some text on it behind my sample, I can see the sample. If we take redness of the oil, again, a critical quality parameter for some, you can see at 50 degrees, you know, we're getting a series of numbers for these different palms, a series of values. If we look at palm number 2, this orange one, my pointer up here, we're getting 3.5, that's dropping probably down to about 3.3. Oh, sorry. And then depending, as we warm the temperature, the sample temperature, the redness value is actually changing. And it fluctuates with some of the other oils as well. And we've had some external customers of ours who've done similar tests and had similar results with their palm oils. If we look at the yellowness here, again, we've seen around 70. We're still getting changes, particularly with that palm oil 2 and that palm oil 7. So you can see that initial appearance of no blue at 50 is not showing the true picture. We need to warm the samples more in order to get a good stable color reading. Now, neutral is an indicator, it compensates for brightness. This is actually interesting what I've shown you here. In that at 60 degrees, you can see we're getting this increase in the neutral reading of this palm oil 2, which indicates the oil is becoming brighter, more transparent. So taking that all together, for multi-fraction oils such as palm oils, you've got to use the criteria for the longest fraction chain present, as the sample may appear melted, but may not be fully melted, and there may be color variation because of the temperature. So when we've spoken with some of the biggest edible oil refiners in the world, and they're recognizing that temperature variation from site to site of sample for critical color measurement, if you want to have a tight tolerance on an automatic instrument, you need to control temperature to get good, consistent color readings. So temperature variation can result in color variation. So to summarize, correct cell path length is critical. It should always be reported. And if the numbers are too high, you need to consider shortening the path length. Oil samples have got to be transparent, particularly with automatic instrumentation. If you're talking about standards, you talk about red and yellow, you need to be talking, check that you're using the same standard as the person you're talking about red and yellow to. Is somebody using AOCS Tintometer? Is somebody else using the Lovibond red, yellow, blue neutral? If you're using a Model F or an AS17, you will have to have wider tolerances simply because of variation between human beings. It's written in the standards. If you've got an automatic instrument, because of the inherent stability of the instrument, there's no human being involved in terms of the direct assessment, you can have tighter tolerances because you've got high repeatability and high inter-instrument agreement. Automatic instruments are fast and compliant. You're not cutting corners. And temperature variation will impact color. Just to say, we appreciate we've got a wide variety of instruments in the market, and our Model FX is designed to have high agreement with both our visual and legacy benchtop instruments like the PFX and PFXi. So if you're in the world of color, we can talk to you about this. I'm on LinkedIn. It's a bit of self-promotion there. Please feel free to connect to me. I'd be delighted. Lovibond.com, a lot of information on there. We have a new edible oils handbook, which includes a lot of the information and much more than what I've discussed today. Thank you very much.
Hey, Matt, thanks for that presentation. We just had one quick question before we move on to our next speaker, and that is the AOCS tintometer scale also logarithmic?
Yes, exactly the same principle as it's not the same as the Lovibond red, yellow, blue neutral scale. So both, which is a common cause of confusion sometimes. There's a complicated long story involving the Second World War and U-boats and all sorts of things, which I won't bore you with. But yes, it's a logarithmic scale and it's not transferable. So you can't take a red from an AOCS tintometer and map it directly onto the Lovibond red. You just need to be careful. We can measure both, no problem.
Yep. Okay. Thank you very much. That's all the questions that we have time for at this moment. We need to move on to our next speaker.